8 segundos.
Vos avísame cuando empiece a compartir la pantalla.
Sí, ya de una vez. Empieza de una vez. Ya te presento.
Empiezo. Okay. Ahora cuando ve que me aparece el cartel amarillo abajo que no me deja.
Listo.
Ahora sí.
Hello, good afternoon. We're starting the last session of these presentations of today. So it's a pleasure for me to introduce you with Federico Holik from the University Instituto Físico de La Plata. And so go ahead, Federico. We have 15 minutes for your presentation and eventually 5 minutes for questions and answers. Thank you very much. Everybody, welcome. Empezamos con Federico Holik. Durante 15 minutos nos da su presentación y al final tenemos 5 minutos de preguntas y respuestas. He's going to be talking about quantum vision. Va a hablar de visión cuántica. ¿En English or in Spanish, Federico?
En español.
En Spanish. Okay, go ahead. Thank you.
Ok, muchas gracias a quienes organizan este evento por darme la oportunidad de dar esta charla aquí. Hoy les voy a comentar acerca de un proyecto de investigación que estamos llevando adelante en Argentina. Para comenzar, voy a dar una formulación del problema. El objetivo es el de estimar el estado de un sistema de múltiples qubits. Este es un problema muy importante y juega un rol central en distintas tareas de la teoría de la información cuántica. En particular, es importante para la certificación de dispositivos. Si se va a vender o comprar un dispositivo, es importante saber si está generando los estados que se promete que va a generar. Entonces, tanto para quien lo vende como para quien lo va a comprar, es fundamental poder certificar que se está generando el recurso o no, y en muchos casos eso implica hacer una estimación del estado cuántico que este dispositivo genera. Y esto es, por supuesto, de interés para la investigación básica, pero también para organizaciones gubernamentales y organizaciones privadas. Porque, bueno, si estas tecnologías se siguen desarrollando, como vemos que claramente está ocurriendo ahora y se espera que esto va a crecer en el futuro, va a ser cada vez más importante desarrollar técnicas de estimación. Pero hay un problema, que es que el número de mediciones necesarias para realizar la detección o estimación de un estado cuántico crece exponencialmente con el número de qubits. Entonces el problema se vuelve rápidamente intratable. Por ejemplo, si tienen 3 qubits y tienen que hacer una tomografía completa del estado cuántico, tienen que medir aproximadamente en 64 bases diferentes. Es decir, tienen que hacer en estadística en distintos contextos de medición. Y esto crece exponencialmente. Ya para 5 qubits tienen que hacer alrededor de 1024 mediciones y así. Crece como 2 a la 2n para detectar estados arbitrarios. Y esto tiene consecuencias. Realizar una estimación completa toma tiempo. Y el tiempo, por lo general, se traduce en un costo económico. Al mismo tiempo, por el procesado de los datos tiene un alto costo computacional, lo cual en muchos casos implica adquirir hardware o contratar un servicio de hardware. Y especialmente consume recursos humanos, porque hay que abocar gente a que procese los datos, desarrolle los algoritmos. Cada dispositivo es diferente. Entonces, y los estados que genera también. Entonces se utilizan distintas técnicas de detección y de estimación o de certificación de que un estado tiene tal recurso o no. Y entonces hay que, bueno, conseguir recursos humanos que en general son costosos, porque se requiere de gente que tenga conocimientos avanzados, no solo de física cuántica, sino de ese problema en particular que es el de la detección de estados. Entonces, estos problemas son especialmente sensibles en muchos países y laboratorios de Latinoamérica, porque si uno tiene un dispositivo, bueno, y está en el MIT, de seguro que va a ser muy fácil reunir un equipo que en unas pocas semanas va a poder resolver el problema. Sin embargo, para muchos laboratorios de países latinoamericanos, incluso compañías, es un problema porque el tema de los recursos es una cuestión sensible. Ya lo vieron en la charla, en otras charlas que se dieron antes, en las cuales, bueno, la zona de Latinoamérica estaba bastante gris, en la cual la inversión en este tipo de tecnologías es mucho menor que la que tienen los países centrales. Entonces, estos problemas se vuelven especialmente sensibles para nuestra región. Entonces, bueno, nuestro proyecto es desarrollar una plataforma para realizar métodos de certificación de estados cuyas características sean, bueno, la primera, que permita estimar estados cuánticos. Y si no es estimar completamente, al menos detectar entrelazamiento u otros recursos que sean de interés para el estudio del dispositivo en particular. Pero lo que es muy importante es que sea accesible a un público general. ¿En qué sentido? En el sentido de que sea lo más plug and play posible, es decir, que pueda ser utilizada sin la necesidad de apelar a recursos humanos que posean conocimientos avanzados de física cuántica, porque estos recursos en general son difíciles de conseguir y cuando se consiguen suelen ser costosos, suelen tener un costo muy alto, tanto para el sector público como para el sector privado. Entonces, la idea es tratar de desarrollar una plataforma con estas características. Es decir, que puede ser utilizada por ejemplo, recursos humanos que vengan de otras áreas que no sean la física, tales como la computación o áreas de la ingeniería que no tengan muchos conocimientos de física cuántica. Entonces, bueno, voy a contar algunos de los desarrollos que nosotros estuvimos haciendo localmente para alcanzar un método tomográfico que sea fácil y sencillo de usar, pero que al mismo tiempo sea efectivo en términos de costos. Una de nuestras principales herramientas es basarnos en estados simétricos. ¿Por qué estados simétricos? Bueno, porque en general estos suelen tener muchos menos parámetros que los estados genéricos, dado un número de qubits. Por ejemplo, en este gráfico que puse acá, en rojo, estoy graficando de hasta 5 qubits la cantidad de mediciones necesarias para hacer una tomografía completa del estado. Esto, como les dije antes, es una curva exponencial, pero si, por ejemplo, si en vez de tomar todos los estados arbitrarios uno se queda con los estados que tienen simetría permutacional, como suele ser el caso en sistemas bosónicos o fermiónicos, la cantidad de mediciones necesarias o la cantidad de parámetros independientes que tiene una matriz de densidad crece polinomialmente con el número de qubits. Entonces el problema, en principio, en ese caso es tratable. Y lo mismo pasa con otras simetrías. Una ventaja del método que proponemos nosotros es que funciona para simetrías arbitrarias. Entonces es un algoritmo que uno le carga la información de la simetría y permite dar una parametrización de la matriz que explota el hecho de que tiene la simetría. Estos estados aparecen con frecuencia en muchos casos de interés, por ejemplo, en sistemas ópticos. En muchas situaciones los bosones, los fotones están en un estado de indistinguibilidad, entonces son simétricos ante permutaciones. Y así, bueno, hay muchos escenarios importantes en donde uno conoce de antemano, no conoce el estado, porque pueden haber infinitos estados con la simetría dada, pero sabe de antemano que tiene la simetría. Entonces, estos algoritmos se basan en explotar el conocimiento a priori que uno tiene de las simetrías. Y en general suelen tener los recursos necesarios para llevar las tareas de información cuántica necesarias. Y utilizamos este algoritmo, es decir, desarrollamos un algoritmo que permite tratar simetrías generales en combinación con métodos de inferencia estadística. En particular con el método de máxima entropía cuántico, lo combinamos con el método de simetrías. Entonces lo que obtenemos acá esquemáticamente a la derecha, pueden ver un gráfico que es una metáfora, ¿no? Uno tiene un espacio de estados que tiene una cantidad de parámetros y ahora esa cantidad de parámetros se reduce, lo cual implica una reducción en el número de mediciones que se tienen que llevar a cabo en el laboratorio, así como una reducción de los parámetros del problema, con lo cual permite además un ahorro en el costo computacional. Ese es el objetivo. Entonces, lo usamos en combinación con métodos de inferencia. Además, Maxent no necesita datos tomográficos completos. Entonces, en muchos casos, uno puede tomar aún menos mediciones que las que se requeriría para llegar a una situación de quórum. Bueno, acá muestro algunos ejemplos. Estos son estados con simetría permutacional. Estoy generando estados de tipo gato de 3 qubits. Si se fijan en esta curva, aplicando el método de Maxent, si uno no considera el algoritmo con simetría, se aplica Maxent, son estados puros. Si uno aplica Maxent simplemente, va a encontrar que alrededor de las 40 mediciones, estos son observables de Pauli, ya alcanza una fidelidad muy cercana al 99%. Sin embargo, cuando considera el algoritmo con simetría, si uno utiliza el conocimiento a priori acerca de las simetrías, rápidamente, es decir, antes de 10 mediciones, uno ya obtiene fidelidades del 99%. No hay nada especial en los observables de Pauli, se pueden utilizar otros tipos de observables y se obtiene un comportamiento similar. Acá, bueno, estoy tirando alrededor de 5 estados, pero en esta curva tiramos 1000 estados, les estoy mostrando, entonces acá tienen el comportamiento sin considerar las simetrías, uno tiene que realizar alrededor de 50 y pico de mediciones, es decir, estadística, en 50 y pico de bases o de contextos independientes, pero cuando en rojo tiene el algoritmo con simetría. Ahí converge a una alta fidelidad, por lo tanto una estimación razonable del estado, con muy pocas mediciones, alrededor de ya a las 20 mediciones ya uno tiene. Y acá tiene, bueno, estoy usando a los estados permutacionales como en caballito de batalla, pero esto funciona para simetrías muy generales. Acá tienen otro ejemplo de estados simétricos, que es los estados de Werner. Supongan que tiene una fuente que tira estados de Werner y ustedes tienen la mala suerte de no saberlo de antemano. Entonces, bueno, si quieren estimar el estado y no usan el hecho de que tiene la simetría, van a tener que hacer alrededor de 63 observables, o al menos 50, para obtener una fidelidad del 90 y pico %. Sin embargo, si uno utiliza el hecho de que el estado tiene asimetría, uno lo carga en el algoritmo y esto permite estimar con muy pocas mediciones. Alrededor de ya con 4 mediciones se alcanza una fidelidad para muchos estados, para la mayoría de los estados generados aleatoriamente, superior al 95%. Entonces la economización es muy grande, la economía de recursos, al menos en el número de mediciones. Y entonces, bueno, esto lo probamos con ruido teórico y es robusto frente al ruido. Simulamos distintos valores de ruido y hemos probado que es robusto frente al ruido. Y acá, bueno, esto no lo publicamos todavía, pero es como un adelanto. Acá muestro, a modo de ejemplo, una tomografía de 6 qubits con ruido. Es un estado HZ, pero podría haber sido cualquier otro estado con simetría permutacional. Es decir, lo único que se asume, el único conocimiento que se asume es que tiene la simetría. Entonces, la reducción que se tiene aquí, si uno quisiera hacer una tomografía completa, tendría que hacer, si el estado fuera completamente desconocido, uno tendría que hacer alrededor de 4100 mediciones para medir tantos proyectores para detectarlo, pero con nuestro algoritmo pasamos a solo 84 mediciones y la fidelidad que obtenemos con ruido simulado es alrededor del 96%. Es decir, con esto quiero decir que se obtienen resultados muy razonables con una economía muy grande en los recursos, tanto de cómputo como de mediciones. Esto esperamos publicarlo en las próximas semanas, al menos tener el preprint. Y bueno, ¿en qué estamos ahora? Tuvimos la suerte de ser beneficiados con un subsidio de Innova CONICET, una cooperación entre el CONICET y Amazon Web Service, que nos permite acceder a Amazon Bracket, a través de Amazon Bracket nos permite acceder a distintos tipos de arquitecturas de computadoras cuánticas en las cuales vamos a testear estos algoritmos para caracterizar su performance y de paso benchmarkear un poco a estas computadoras y ver cómo están funcionando. Entonces, para terminar, nuestro objetivo es entonces desarrollar una plataforma para realizar métodos tomográficos y de certificación que sean accesibles a un público general, es decir, un público que salga más allá de la física, es decir, que no necesariamente tenga conocimientos avanzados de física cuántica, y desarrollamos un algoritmo que permite explotar simetrías arbitrarias de los estados. Y a este algoritmo lo combinamos con métodos de estimación que permiten reducir aún más el número de mediciones necesarias y aún así obtener una fidelidad decente respecto del estado que uno quiere detectar. Probamos con tomografía cuántica variacional por ahora y con Maxent y los resultados son muy promisorios. Y otra característica que es clave de todo este algoritmo es que es bastante sencillo. Desde el punto de vista matemático, hay una cuestión de teoría de grupos que puede llegar a ser compleja para más de uno, pero a nivel algoritmo es bastante sencillo. Entonces nosotros queremos ponerlo a punto para publicarlo y que sea accesible al público más general posible. Esa es nuestra idea, hacer que el método de detección se vuelva accesible a sectores cada vez más amplios para acompañar el crecimiento de estos desarrollos tecnológicos que seguro se van a dar en los próximos años. Entonces, bueno, en los próximos meses esperamos avanzar en la implementación y testeo de estas variantes de algoritmos, de forma tal de hacerlos de fácil uso, sea rápido y accesible. Bueno, aquí tienen algunas publicaciones. Para ver los detalles de esta charla, les recomiendo ver este último paper que va a aparecer pronto en la revista Quantum Information Processing, está en prensa, pronto estará. Si quieren ver los fundamentos teóricos, conviene ver por ahí el primer paper y también el segundo, en donde está la aplicación al caso de información cuántica con sistemas de múltiples qubits. Bueno, eso es todo. Muchas gracias por su atención. Quien quiera preguntar un comentario me pueden escribir a esta dirección de email.
Excelente, Federico. Muchísimas gracias por tu explicación, brillante explicación. Muy interesante ver cómo una asimilación de un modelo teórico puede llevar a una implementación. Y bueno, felicidades por el grant también con Amazon, que seguramente te va a dar mucho más información, sobre todo experimental, que puede compartirse también a toda la comunidad. Muchas gracias. Muy consciente de los problemas que mencionas y las ventajas de utilizar este tipo de metodologías. Felicidades, realmente, muchas gracias. ¿Alguna pregunta que quieran hacer, Federico? Yo creo que está muy claro el planteamiento y seguramente gracias por tu correo electrónico va a haber preguntas interesantes y sobre todo que dé pie a colaboraciones. Hay que aprovechar que ya tiene el funding de Amazon Web Services para hacer más experimentos, ¿no?
Claro, por supuesto.
Gracias, Federico. Gracias.
Gracias a ustedes, gracias a ustedes.
Un aplauso fuerte, gracias. Bien, pues ganamos un minutito. Si les parece, vamos a empezar con Fabiola Cañete, que nos va a hacer favor de hacer su presentación. Ella es estudiante de la Benemérita Universidad Autónoma de Puebla en México. Do you like to offer your talk in English or in Spanish, Fabiola?
I think in English.
In English. Okay, great. Go ahead.
Yeah.
So we are going to have the presentation of Fabiola in English. So you have 15 minutes for your speech and try to save 5 minutes for questions. So go ahead. Thank you very much for coming today.
Thank you. So, can you see my screen?
Not yet.
Mm-hmm. What about now?
No.
It says it is loading. I don't know why. It's not showing yet.
You have to choose on the right, sharing, compartir pantalla, and then choosing directly your slides.
Okay, let's see, share screen. No.
Try sharing your entire screen, please.
Yeah. Share. Okay. Yeah, this is what I'm doing, but I don't know why it's not working.
Is it PDF or it's PowerPoint?
It's well, the version in iOS operating system. It's slides.
Yeah.
It's like PowerPoint, but yeah, it's not working.
Maybe when you are choosing your entire screen, just to share, choose your screen and then put it share. De todas las que aparecen tienes que seleccionarla y luego le pones share, aunque sea solo una.
Okay. Yeah, sí, eso es lo que estoy haciendo, pero no sé por qué.
Is Chrome or Edge?
Yeah, it's Chrome. Yeah.
Chrome, okay.
Yeah, that's what I'm doing. I don't know why. Yeah. Well. Share screen. Let's see if this works. No, it's not working. How about
if you have Edge, maybe you can try with Edge instead of Chrome. Do you have it in the web? Maybe
yes. No, in the web. No, I don't have it. Give me a few minutes. I will connect.
Okay.
Again. Yeah, please.
No worry. Yeah.
Okay, this works. Is it visible now?
Yes.
Oh, thank God.
Got it. Okay, thank you.
Okay, thank you so much. Sorry for the delay. So, hello, my name is Fabiola Cañete Leyva, and I am a physics undergraduate student at Universidad. I am doing my thesis project under the supervision of Dr. Salvador Venegas Andraca and Dr. Carlos Pérez Delgado. And today I'm going to talk to you about a quantum search algorithm for performing proof of work. So the objective of this talk is to present some of the advances of the project so far. And for that, I'm going to talk to you first about some background concepts like hash functions, the proof of work mechanism, and also about Grover's algorithm, which is one of the most known quantum algorithms and the one that we are going to use in order to solve the problem that we are addressing. So let's start with hash functions. So in the digital world, it is of great importance to have a system that allows us to communicate securely. And that is why numerous ways of protecting the information transmitted have been developed over the years. These tools are mainly based on encryption methods that are used to generate passwords, private and public keys, digital signatures, etc. So one of the tools that has been created for this purpose was developed approximately in the 70s, and it is called a cryptographic hash function. So cryptographic hash function is a function that takes a string of arbitrary size as an input, and it outputs a string of fixed length. So this last string is usually known as the hash value. And there are several properties that a hash function needs to satisfy in order to be secure. But the three most important ones are called pre-image resistance, second pre-image resistance, and thirdly, collision resistance. So I'm going to talk about them. Pre-image resistance ensures that given a hash value, it will be very difficult to find the original message. This is the pre-image, the input. And second, pre-image resistance ensures that given a message and a hash value, finding another message with the same hash value is going to be very difficult. And finally, collision resistance ensures that it will be very difficult to find two messages with the same hash value. As mentioned before, cryptographic hash functions, they are present in several security protocols, and they actually have a very important role in the mechanism of proof of work. that occurs when mining cryptocurrencies like Bitcoin. So in the year 2008, Satoshi Nakamoto published a paper that describes how we can use blockchain technology in order to solve the double spending problem. And in this way, he created what we know now as the concept of Bitcoin, which is a decentralized digital cryptocurrency that can be transferred on a payment network. And so a blockchain is a distributed database that groups transactions into immutable digital signed structures called blocks. And in principle, any participant of the network can introduce a transaction to the ledger. All the transactions that happen in a given period of time are aggregated to the same block, which is linked to the previous one through the use of a cryptographic hash function. So let's see how the Bitcoin transaction cycle works. Let's suppose that Alice wants to send a transaction to Bob. So she will have to use the public key of Bob, and she will also have to determine the amount that she wants to send to him. And when she decides this, she is going to broadcast this information to the network. And the nodes of the network are responsible for validating this transaction. And after this, they will perform a mining mechanism. So we call mining to the process of adding new blocks to the chain. And the process is the following. A node or the miner, he will select a set of broadcasted transactions. He will also select the header of the most recent block. And after verifying that the transactions are valid, he will perform what we know as a mechanism of proof of work, which is a consensus mechanism. So once the miner has encountered a solution to a given computational problem, he will broadcast the new candidate block, and if this candidate block is verified, then it will be added to the chain. After this, if everything goes smoothly, Alice will receive a confirmation message. So here we are interested in the proof of work mechanism. During this process, the miner will concatenate together the header of the most recent block, the information of the new transactions, and also a nonce, which is a random string of fixed size. And he will hash everything together. And so proof of work requires the miner to find the hash value under a given target. And this task involves expending a lot of resources in trying to find a solution for this computational puzzle. And this will require no skill, but only brute force. So the idea of using a quantum algorithm for performing proof of work is really interesting. So proof of work can actually be solved with a search algorithm, which is going to help us find the nonce that will output the hash value that we are looking for. Search algorithms answer to one of the most fundamental problems in computational science. And in this kind of problems, you have a set of possibly disordered set of n elements. And the objective is that given a function f, to find the element that represents the solution to our problem. So classically, this problem requires, in the worst case, n evaluations of the function f. But there is a quantum algorithm which solves the same problem in square root of n queries, and this is the Grover's algorithm. So the Grover's algorithm basic structure consists of the superposition of all the states that are going to represent the domain of the function, and will also consist of the performance of several Grover iterations, where each iteration consists of the application of an oracle and a diffuser operator. So the idea of performing proof of work was discussed in a paper by Bard and others, but actually there was no explicit algorithm given, and that is the problem that we choose. The first step of this project is going to be to develop in detail this algorithm. So for this, in order to find the actual advantage of this quantum algorithm over a classical algorithm, we decided to develop the quantum circuit, and obviously this will have to include the performance of cryptographic hash function SHA-256. And for this purpose, we developed also 4 protocols that have to be included in our Grover iteration. So the first protocol, we call it pre-processing protocol. And at this stage, we will initialize the qubits that we are going to use to represent our message. Then we will perform a padding scheme, which is the first step of the cryptographic hash function. And also here we are going to perform the superposition of all the states that represent the nonces. The second protocol is called the message schedule protocol. And here we will create the variables that the hash function needs from the qubits in the first protocol. The third protocol, we call them a compression loop. It's here is where the main calculation of the hash function is done. So the result of this protocol will do the main calculation of the hash value that is associated to the message and to each one of the nonces. And finally, the fourth protocol will perform a comparison between the values that we calculated and the target value. And so overall, we estimate that we will need 5,000 logical qubits to do this. This is the first version of the algorithm, and we expect to improve it, of course. But yeah, this is one of the advances that we've got so far. And this is it. Thank you for your attention. I hope you find our work interesting. Thank you.
Amazing, amazing. Thank you very much, Fabiola. It's a very, very clear explanation. Actually, I think it's very nice to see on those pictures how you can justify the evolution of something and used to be very complex to understand as the blockchain, and it's used to be confused with cryptocurrencies, but at the end it's a distributed ledger strategy, and the proof of work is still a very interesting problem to analyze with this new point of view of quantum computing. Thank you very much for your nice explanation. I don't know if we have some questions that people like to ask to Fabiola. Yeah, maybe a little bit about the foundations of blockchain, because actually the procedure of verifying and broadcasting the information and to ask the miners to carry on all the algorithm verification involves as well a cryptographic phase that used to be used with the state-of-the-art algorithms. And in certain point, we are going to be confronting the new advances of quantum computing with this proof of work. I don't know if you can expand a little bit that idea. We still have 2 or 3 minutes, so maybe you can give some more thoughts about your proposal.
Yeah, well, a lot of people ask if Grover's algorithm is able to break the blockchain, right? Because if you have this power of computation, you will, in the network, you will be able to dominate over the network, and you will be able to forge blocks, falsify information. And so this question is also addressed in the paper that I mentioned. We expect that this can happen, of course, but in the states that we are in the development of quantum computing, we do not expect that this is a very close danger, like it's not very near, but it can happen. Yeah. So yeah, this has to do also with the resources that you spend when mining cryptocurrencies like Bitcoin, for example. You have to spend a lot of computational power, electricity. It has also to do with the power, the hash rate, and the difficulty of the target. And a lot of people is wondering, little people are wondering about the future of cryptocurrencies like this one. Yeah.
I will be delighted in reading your final thesis. I'm sure that should be fantastic and interesting, your explanations about it. So thank you very much, and congratulations. So if we don't have any other questions, just to say you thank you very much for your time.
Thank you.
Very clear and amazing explanation. So thank you very much.
Thank
so
you.
let's move with Kevin Vallejo. Actually, Kevin is already with us today. Kevin is a postdoc at Idaho National Lab, if I can see correctly here. So welcome, Kevin. Do you like to offer your talk in Spanish or in English?
I think I'll give my talk in English, please.
Okay, thank you very much, Kevin. So you are already sharing your screen. So go ahead. You have up to 15 minutes. We recommend you 15 minutes on your speech, and then open to 5 minutes for questions and answers. Go ahead. Thank you very much for your presence, Kevin, today.
Okay, thank you very much. Thanks for the invitation and for organizing this very nice symposium. I have been very happy to see all the efforts and future work that is being planned for Latin America on the quantum realm. So I'm also pretty happy to see that I'll probably be one of the only ones that is going to be talking about the materials that we need to actually realize all of these new quantum paradigms and quantum computers that we're planning and that we're developing algorithms for. So the talk that I'm going to be presenting to you today, it's on how to make these nanostructures based off semiconductors that we call quantum dots through a method that allows us to not need to move the substrate or pattern it in any way. All we need to do is use a special technique that lets the quantum dots form by themselves that we can then assemble into these quantum circuits and quantum cavities. So with that, I will give you just a quick overview of the talk in Spanish so that we can all be on the same page. First, I'm just going to give you a little bit of motivation. I'll talk about the versatility of the technique, which is epitaxia por haces moleculares, or MBE, molecular beam epitaxy. I'll talk about the homoepitaxy of this special material that I selected for some of my graduate work, which was indium arsenide, or arsenuro de indio. I'll talk about quantum dots. I'll also talk a little bit about what we did about the material of the quantum dots on this system, some trial and error in material selection that led us to actually finally realize these quantum dots with the properties that we expected them to have. And maybe I'll have a little bit of time to discuss a little bit of the dynamic quantum dots that we're envisioning will be really useful for new qubit circuits. Okay, so what areas benefit from the study that I performed? Well, quantum nanostructures, infrared photonic devices, high index crystal growth, and atomic level computer modeling. So all of these are strongly correlated, and they all have one thing in common. They have this semiconductor growth aspect to them. So with that, I want to tell you about how do we connect this quantum dot technology that I'm working on to the actual quantum computing and quantum information paradigm that we're expecting in the next few years. Well, there's a whole book about it, Quantum Dots for Quantum Information Technologies. I'm sure some of you might even know the author of this book or some of the authors inside. But these semiconductor quantum dots, to which I'm going to talk about, can be useful for stationary and flying qubits. They let us generate, manipulate, and control charge carriers. They're an excellent, if not the best source for single entangled photon states. They also let us study in great detail light matter interactions, as well as spin photon entanglement phenomena. So There is a big distinction that I need to know. I need you folks to know. When you go to an electronics hardware store and you want to buy this fancy new TV that is quantum dot technology, they're not actually talking about the quantum dots that I will talk to you about. Those are mainly quantum dots that are either fabricated or produced into these consumer electronics through a solution approach. So this is a relatively old technology compared to the things that we're talking about in this symposium. And they primarily synthesize chemically, which often leads some organic or other impurities in the quantum dot, making them not as perfect as we could make them. In contrast, the technique that I'm using focuses on solid-state quantum dots, which can be made strictly from the constituent elements without the need to actually have to use a compound that then will chemically break in order to make the material that the quantum dot will be made of. So much for the motivation and the presentation. What do we actually did? What did we do for this job? Well, we used this technique called molecular beam epitaxy. What does it do? It approaches to perfect crystals. It is a complex system, and there is a lot of companies. I know that Microsoft, IBM, and Google, they all are focusing their efforts on these high vacuum epitaxy techniques that let us make these materials. So just a little break of this, the fanciest word on this slide, which is epitaxy. This one essentially means that we're creating order from above. Comes from a couple of Greek root words. And the main thing about molecular beam epitaxy is the amount of vacuum that we need. We need to start with a scroll pump, which takes us from atmospheric pressure down to like 5 times 10 to the negative 6 torr. So already we decreased 8 orders of magnitude our pressure. This is where we load the sample. Then we move into a different chamber. We're using an ion pump. We reduce the pressure by 3 more orders of magnitude. From here, we pull our substrate onto the growth chamber, where we have it in this high vacuum of 510 to the negative 11 torr on a good day. And in there, we have it interact with effusion cells. These are essentially tiny ovens where we have 99.99999% pure elements that fly because we heat them and hit the substrate. This allows us to have the most perfect material that we can possibly get. Once we have this sample, we need to focus on what makes the sample that we want the sample that we want. How do we tune these parameters? Well, there's 3 main parameters that we need to care about. These are the substrate temperature. This is how hot do we need to have our substrate so that the atoms will stick to it. We need to focus about the atomic flux pressure. How much do I need to heat these elements so that the pressure that hits the substrate is the correct one?
So we can just wait some seconds. Vamos a esperar un poco a que Kevin pueda conectarse nuevamente. Ahí viene otra vez. Adelante, Kevin. Gracias.
Perfecto. ¿Me escuchan bien?
Sí, adelante. Te perdimos 30
All right.
segundos.
I don't know where I stopped, but the bottom part of this slide tells us that we have parameters that we can connect from the things that we move in the MBE versus things that will determine the quality of the sample. Feel free to ask any questions about anything that I may have explained to the void while I was disconnected. Okay, quantum dots, puntos cuánticos. These are essentially zero-dimensional structures. What do we mean by zero-dimensional structures? We mean that the charge carriers, electrons, holes, maybe even spin little quasi-particles, cannot escape this confined volume that we generate by creating a small bandgap material inside a large bandgap matrix. This is essentially an artificial atom because atoms in nature have already determined their energy levels. By tuning the volume of this artificial atom, we tell it what color of light it should emit. and also how pure will the light coming out of this quantum dot will be. So what do we want to focus on? Well, we want to focus on this region of this whole map where we have materials that relate their band gap energy. This is how much energy do I need to make an electron go from a regular state into an excited state. And the lattice constant. This is the distance between the component atoms of my sample. I focus this study on the gallium arsenide, indium arsenide, and gallium antimonide system for a few reasons that I'll highlight in a little bit. So, first step, homoepitaxy of indium arsenide. While I was doing my graduate studies, I realized that no one had actually put the effort into finding out how do we do this 1-1-1 to see what the growth rate will do to our samples. We determined that the initial growth rate, which was 0.12 monolayers per second, was actually ideal. Going faster makes it worse. Going slower makes it worse. So we just stayed within this growth rate. And then we determined how much of the arsenic element, this is the element from the 5th period of the periodic table, versus indium, an element from the 3rd period of the periodic table. The ratio of the pressures is also a very high factor because it determines how well the atoms will stick. So we determined that the higher this ratio, the more arsenic we have floating around, the better for our samples. Okay, we have an even playing field, literally. Now we want to nucleate these quantum dots in there. So we go with our indium gallium arsenide material. We start by depositing 3 monolayers. This is, you have indium and gallium alloy, and then you have an arsenic. So by doing just 3 layers, 3 atom thick layers, we see that our beautiful smooth surfaces actually turn into these tiny islands that you can see here. And the more gallium we put, the more quantum dots are created. This is because we're increasing the tensile strain, and this makes the quantum dots want to nucleate more. So we tried a few things. We did some temperature play, and then we wanted to make sure that this was actually quantum dots all over. So we did some quantum dots on the surface, quantum dots kind of buried under a indium arsenide cap, and using transmission electron microscopy, we found out that we have these beautiful strained states. We have quantum dots that we can protect from the environment. And then we need to make sure that they're quantum dots. And how do we do this? Well, they have to emit light. We have to make sure that there is confinement of the charge carriers. Unfortunately, indium arsenide does not provide enough of a barrier for the states to be confined. And so these were not quantum dots. These are simply nanostructures. So we had to start from the beginning. Let's move from indium arsenide onto gallium antimonide. We did the same things, play with substrate temperature, 5/3 pressure, growth rate. We managed to get these beautiful flat, atomically flat surfaces, beautiful crystal structure with TEM. And because we had a few different elements now, we had to play with when are we going to let antimony go in? When are we going to let arsenic be in? How are we going to purge them from the chamber? We determined a few of these parameters, and we got, again, these beautiful quantum dots nucleating, this time on gallium antimonide. You can see this SEM scan where we see these beautiful triangular features, which are a signature of our 1-1-1 surface. We were able to map how much material deposited, how does it affect diameter, how does it affect height. But the very interesting thing is, can we get light out of them? Well, if we were to, we needed to make sure that the buried quantum dots were also protected, like in the previous one. And we noticed that, yeah, they are protected. They're beautiful strain features down here. We can confirm that the presence of indium, arsenic, just a tiny bit of antimony was inside these quantum dots. So we moved to the fire trial. Do they emit light? And we're happy to report that they do emit light. We were able to report the first quantum dots that were self-assembled to emit in the mid-infrared part of the spectrum. We have a correlation, and right now we're running the calculations that will allow us to correlate this size of the quantum dot, their composition, to the light emission that they're producing. But the fact is that we actually managed to get these quantum dots to emit light. So what is next? Well, now that we have the light emission, the next step will be to make an LED or light emitting diode based on these infrared quantum dots. Then we'll have the ability to create a cavity for controlled light emission. And this will be our chance to actually integrate it together with other qubit architectures for new circuit designs. So as acknowledgements, I want to acknowledge all these people that were giving us money for our studies, some of our collaborators that are in Mexico, some of our collaborators that are from other countries working in these universities in the United States. And finally, I want to give thanks to the Idaho National Laboratory that led me to present this to you guys. Thank you.
Thank you very much, Kevin. Very nice, very clear. And as you mentioned, it is an amazing topic, how to deal with the materials research for the future of the kind of computers we are expecting to have, and you carry on quantum information and computing processing. So I'm open the meeting for anyone who likes to ask any questions to Kevin. We have some time to do that. If you like to
just
do
one at a time, please.
Yeah. You like to make a question in Spanish? He's completely open to receive it as well. Yeah, in between, I have some questions about the quantum dots. Do you have an idea of any specific eventually function that we can take into account from the quantum dots for the quantum computation? Is there any relation in between the quantum dots to eventually the quantum information processing?
Yes, absolutely. Depending on the type of qubit that you want to use, the quantum dot can use the charge carrier, the electron, to make your channel. It can do single photons, entangled photons. It can also be used to be the wire in between some other architectures like a neutral trapped ion, or some ultra cold interfaces between oxide and semiconductor. So the quantum dots have this ability that give us very precise control over current and future architectures on quantum computers.
Okay. Yeah, because I have read a lot about it, but I never think about how we can use it. If there is any particular numerical operation. We have listened a lot about the Fourier quantum transform, and eventually with the disruption of multi-layer systems, we are actually moving from convolutions to carry on convolutions in those spaces, and seems to be a natural signal processing method that can be used with eventually quantum dots. Well, I don't know. We have any questions? Any other questions, or something that you like to expand a little bit more, Kevin? We have 2 or 3 minutes more.
Not particularly. I'm happy to answer any questions anyone may have. I see that this a more hardware related talk than the previous ones, but hopefully we'll have a more connected hardware materials all the way down to like the actual implementation of algorithms by next year's conference.
Yeah, I have maybe something that you can share with us. This Idaho National Laboratory, do you have any specific challenge in mind about the building of quantum gates or quantum circuits in particular, or you are doing basically basic research related with those models?
So most I would say all of my research is actually basic research. There is not a specific mission towards quantum computing at this laboratory, because we are the nuclear energy laboratory in the United States.
Okay.
But we do have the ability to collaborate with other laboratories that have that might need our material processing capabilities to have the research program advance.
Okay. Well, maybe you can share your email somewhere. You have your email in some slides that can be useful eventually if someone likes to get in contact with you. Anyway, we have all the information about the speakers. So I have this mention about excellent presentation, Kevin. Thanks. So thank you very much, Kevin, for your nice presentation. Congratulations, and hope to see you early, at least next year again. Thank you very much.
Absolutely. Thank you, everyone.
Okay, next speaker is Allan Wing Bocanegra. I don't know if Allan is already with us.
Hola.
Hi, Allan.
Hola.
How are you today? Oh, we have Professor Salvador Venegas too. So if you'd like to introduce Allan, Salvador, please go ahead.
Yeah, thank you very much. Hello, Allan. How are you? Hold on, please. So we're live, right? Yeah, we are. Okay.
Yes.
Yeah, hello. How are you? I'm very happy to be here with you again. It's my pleasure to introduce Allan Wing Bocanegra, who's an MSc student at Tecnológico de Monterrey, and his talk is entitled Circuit Implementation of Coin Quantum Walks via the Shunt Decomposition Method. Go ahead, please. Thank you.
Okay, thank you, sir. 1 second, let me share my screen. Okay, so can you see my screen now?
Yes, indeed.
Okay, perfect. All right, so yes, I'm going to speak about the quantum circuit implementation of quantum walks. So first, I'm going to introduce a little bit about graph theory. So a graph is a collection of nodes and edges, or arrows that are connected, and an adjacency matrix is just a matrix representation of the information of the connections between the nodes in the graph. So here, for example, for those who are not familiar with the topic, if we can see that node 0 is connected to node 1, and we represent that by choosing the row 0, and then choosing the column 1, and then we put a 1 there, and we follow the same procedure to for the other connections between the nodes, and we end up with this arrangement with the adjacency matrix. All right. So why is it important to know what's the information that an adjacency matrix contains? Well, because it allows us to perform a quantum walk. Here we use a person, or the model tells that we have a person that is standing in a certain coin. In a certain vertex. Then the person tosses a coin, and according to the coin, they move to the right or to the left, depending on whether it's heads or tails. And we use a probability vector that tells us, the number of the entries tells us in which vertex this person is standing on. Right. So we apply this matrix, and then we get the probability distribution of the person after touching the coin. In this case, just as an example, this person moved to the right, and here it tells us that the person has 50% chance to move to either node 1 or node 7. And for n steps, we apply just matrix A and times to the initial probability distribution vector. So a quantum walk takes that idea and makes a little difference, because we do toss a coin, but we have a quantum coin. And here in this GIF, I intentionally selected this special GIF because in this GIF the coin never stops spinning. So that's the idea in a quantum walk. It has a coin, but we do not know the information of the coin or of the state of the walker until we perform a measurement, but we don't do it until the end of the walk after having performed n steps. All right. So the first step is tossing coin. The walker gets into a superposition of two states, and say we use different colors for each direction. So say the black person moves to the, or the black state moves to the left, and the white one moves to the right. After that, we apply a displacement, but in this case, because the coin we never know what's the result of the coin, we assume it's actually both heads or tails at the same time. So we move both to the right and to the left. Right. So the quantum definition of a quantum walk, the mathematical definition of a quantum walk is given by a bipartite system. That's the state of a walker that consists of a coin state and a position state. Then we have an evolution operator, which consists of a coin operator and a shift operator, which we will see later that operator is the one that contains the information of the links between the nodes of a graph. And then we have a measurement operator, which is applied at the end of the walk, and we obtain the probability of a person being in vertex J by performing this operation. Okay, so now, well, it is already known by physicists who work in statistical quantum mechanics that unitary operators that are applied in bipartite system have this form, in which we have a matrix that is composed of block matrices. And it turns out that these block matrices, or the columns of these block matrices, are sets of Krauss operators. Each column forms a set of Krauss operators. And the Krauss operator is just an operator or transformation of quantum state that is given by this rule. Right, and K is the Krauss rank. In the case, first, the general decomposition, or this allows us to see the adjacency matrix of a graph. The shift operator of a graph of a quantum walk as a kind of a kind of mapping of the adjacency matrix of a classical random walk to a quantum system, because we're transforming this random matrix into a unitary operator by decomposing it into the sum of many Krauss operators. Okay, so in the special case in which all the columns form or have a Krauss representation that has rank 1, we can arrange those operators, which are now unitary, in the diagonal of the shift operator. Right. So this, as we will see later, this will easy a lot the transformation to the circuit form, and also the sum simplifies to just this. The decomposition of A simplifies just to the sum of m unitary matrices, and this is called the Shunt decomposition. It was, the name was given by Sun in 2019, this paper, and Montenegro also worked on the decomposition, on the additive decomposition of adjacency matrix. So if you want to do a further reading, you can read those papers. All right. So why is it important? Because as I said before, this simplifies a lot the implementation in circuit form. If we study the matrix representation of a fully controlled quantum gate, we can see that it is also a block diagonal matrix, right? And we assume these dots, which are the control qubits, or we just call them controls. We can try to see them as a string of bits, right? So in this case, the 0 is represented by a white dot, and a 1 is represented by a black dot. So in this case, we have a string with 3 1 dots. I mean, 3 ones. So that's 7 in binary. So that means that this gate has this matrix pi in the 7th, in the 8th position of the diagonal. So if we want to build a circuit that has this structure, we just have to get 8 permutation matrices. So in this case, I didn't mention it, but permutation matrices are a special case of unitary matrices. So because A is almost always a irreal matrix. So it is I think it is. How do you say that? We just have to decompose it into a sum of permutation matrices, right? There's no need to go to complex matrices. So if we get 2 to the n matrices, or 2 to the n gates like this, and we place them together into one single circuit, their matrix representation will be given by the product of your corresponding unitary gates, such as this one, and we obtain the Shunt decomposition of a quantum walk, or of a graph. So an example is given by the complete graph with 4 vertices. And we can see that this is the adjacency matrix of this graph. We can see that we can decompose this graph into 4 unitary matrices. And these 4 unitary matrices correspond to certain subgraph into the whole graph, as can be seen evidently by the colors. So in circuit form, these matrices are easy to obtain. And this one is represented by the tensor product between 2 identity matrices, and this one we put a C0 in the first qubit and an identity in the second one. This one is represented by an identity and a C0 in the second qubit, and the other one is represented by a C0 gate in each of the qubits. All right, so we control those gates I just showed you, and we obtain the shift operator of this, to perform a quantum walk into this graph. All right, and as I mentioned, these matrices are placed into the diagonal of the operator S. So we use this method to apply it to some common topologies that are usual in the field of quantum walks. So here, by example, we took the case proposed by Shaquille in his paper, and we studied that this implementation lies in the method that we proposed, and then we performed three models to run them into IBM Quantum Composer using 4 quantum computers, IBM Q Quito, Lima, Bogota, and Manila, using 8,192 shots. So here are the results, and here in the first row we have the theoretical results, and here with the first model, which is the long-range arrangement, we can notice that it has pretty much the same distribution in the other ones too, but we have a little errors here. But overall, we have the states with the most probable distribution, or the most probable with the greatest probability, are the ones that correspond to the theoretical ones. In the case 2, we have a similar case, and in the case 3, we also have a similar case, but in the first 2, but not in the quantum Fourier transform circuit. All right, so after that, we also came up with a circuit that is able to perform a quantum walk in a cycle graph of any size. The other one, the circuits are able to provide a quantum walk for it to the end cycle graph. But if we want to have some other number of nodes, that circuit will not help us to perform the walk, but instead we provided a sequence that is able to do that. Here I did not show the whole sequence because there are a lot of circuits, but here I provide an example with a 5-cycle graph. All right, but unfortunately, because these IBM's quantum computers are not efficient to run circuits using many control qubits, so unfortunately we did not get good results using these circuits. So we just didn't show the results. Okay, so then we have an N-cube. This circuit was proposed by Douglas and Wang in 2018. I forgot to add the reference, I'm sorry. And well, it turns out that we studied a little bit about this circuit, and they proposed a circuit for a 2 to the n cube. But we realized that if we take out the last CNOT gate, the one with the longest range, we can obtain an n-cube, but for lower dimensions, right? So, by example, here we have the quantum circuit that performs a walk in a 4-cube. But if we want to perform a quantum walk in a 3-cube, or in just a regular cube, we have to remove this gate. But instead, we will have a quantum walk in 3-cube with self loops. So we can change the topology, or we can change the connections between the vertices in the quantum walks by taking out certain parts of the circuits, but we cannot decrease the number of arrows coming out of each vertex. So that's why we end up with a 3-cube, again with four arrows coming out of each vertex. And well, this is the circuit of this 3-cube. We also ran it in the same quantum computers, and we obtain distributions that are similar, at least in the first 2 steps, to the theoretical ones. Complete graph. Here's this quantum circuit that we obtained. This is just an example for a graph with a complete graph with 8 vertices. But it turns out that this circuit can simplify applying certain techniques that are already known in the literature of quantum circuit synthesis. So, by example, if we have multi-control, multi-target circuits, we can simplify them as this. And if we have circuits which have the same target gate and only differ by two controls, we can simplify them as this. And well, applying these rules to the whole quantum network, we simplify the circuit to this sequence of gates. If we want to build a quantum circuit for higher dimensional to the n complete graph, we just have to follow the sequence and add more CNOT gates. All right, so experimentally we perform the quantum walk using this a lower dimensional graph, which is a for complete graph, the one I already showed you, and we compared our version to a version already proposed by Douglas and Wang, which basically follows the same sequence, but instead of having CNOT gates, they use swap gates. And well, we can see that essentially we get similar results in all the steps, but not in the third one. In the third one, we obtain good results in both steps, but we can see that even theoretically the resulting state, or the resulting state after 3 steps changes. So that means that even if we perform, that means that the mapping of an adjacency matrix to a shift operator is not unique. And even if we have a shift operator to perform a quantum walk in the same topology, the dynamics of the walker in that topology will not be the same. So this is a proof of that. So yeah, conclusions. We get that the shift operator is just a mapping of the adjacency matrix of a certain graph, and we shift operator by using the Shunt decomposition. And well, in the case in which S is a block diagonal matrix, we already presented a method to map it into circuit form. And then we use this method to implement efficient quantum walks into common topologies. All right, so that's the presentation, and that's the work I've been developing these years. Thank you for your attention. So, if you have any questions.
Thank you very much, Allan. It's been a great presentation. Thank you very much. I think we shall, stop now with your talk and give a 1-minute break, because the incoming speaker is just right here with us, Isaac. So thank you very much again, and see you soon.
Okay, thank you.
All right. Hello, Isaac. How are you doing? I think it would be a good idea to start trying out showing your screen.
Yeah.
So if you could do that now, it would be great. Thanks a lot. And then I'll introduce you. But before, please try out the screen your presentation.
Yeah. La presentación, bueno, está en inglés, pero pensaba hablar en español, si no hay problema.
Sí, perfecto, ¿no? Hay total libertad de hablar en inglés, español, portugués. En Quantum Latino 21 tuvimos, de hecho, si mal no me acuerdo, una plática en francés también. Pues las lenguas del continente son bienvenidas, por supuesto.
A ver. Me parece que está cargando, pero no sé si...
No. No está cargando. No se ve.
O sea, aquí me parece que está cargando, pero no sé.
Ok, pues esperamos un momento.
Ya.
Y ahí va, exacto. Very well.
Bueno,
Ok.
Dígame si cambió ahí.
Sí, ya se ve bien la pantalla, gracias. Tu presentación ya se ve. Bueno, entonces, permíteme que te presente rápidamente.
Sí.
Y,
¿Abro cámara?
sí, si gustas. Bien, pues, muy buenas tardes a todos. Esta es la última plática de Quantum Latino 2022. Muchas gracias a todos por este fantástico viaje, porque hemos estado durante 3 días hablando de diferentes aspectos de la tecnología cuántica en nuestro subcontinente, de lo que hacen otros latinoamericanos en otras partes del mundo. Quiero agradecer de todo corazón la participación de más de 500 personas registradas en este evento de Quantum Latino 2022. Pues bien, la verdad que me quedo sin palabras. Ahorita hemos de hacer, de hecho, la conclusión oficial, así es que no me adelanto, vamos a estar participando en la doctora Venegas Gómez, entre otros, en la conclusión. Y ahora, pues para cerrar con broche de oro, vamos a escuchar a Isaac Geovany López Ramírez, a quien tengo el grandísimo honor de dirigir su tesis de maestría, como también es el caso de Allan, quien acaba de presentar. Isaac va a hablar sobre, bueno, el título de su plática es The Fourier Transform Qubit Representation as Encoded Method in a Variational Quantum Image Classifier. Isaac, muchas gracias por estar aquí y pues adelante, la palabra es tuya.
Sí, estimado, muchas gracias. Pues brevemente me vuelvo a presentar. Mi nombre es Isaac López. Estudié la carrera de Ingeniería Física Industrial en el Tecnológico de Monterrey y actualmente estoy estudiando la maestría en Ciencias Computacionales con especialidad en aprendizaje automático. Y pues les quiero presentar un poco de mi trabajo en la tesis, que como dijo el doctor, está siendo supervisada por el mismo doctor Venegas. Y pues sí, el título es la representación de qubit de la transformada de Fourier como método de encodificación para un clasificador variacional cuántico. Bueno, primero quisiera poner algo de contexto sobre el tema. Después quisiera brevemente explicar lo que es un clasificador variacional cuántico. De ahí explicar lo que es la representación de imágenes cuánticas, hablarles un poco acerca de lo que estoy haciendo y las motivaciones, y por último terminar con conclusiones y trabajo futuro. Entonces, el área en la que me estoy desempeñando es visión por computadora. Es una área de inteligencia artificial que trata de permitir a computadoras y sistemas derivar información importante acerca de imágenes digitales, videos y otras entradas visuales, con el propósito de tomar acciones y de crear recomendaciones basadas en la información que otorguen. Y esta área pues tiene muchas aplicaciones, van desde la detección de objetos, desde la segmentación semántica y por supuesto la clasificación de imágenes. Y bueno, hablar de visión por computadora es hablar eventualmente de las redes neuronales artificiales. Son muy famosas. Brevemente, son nodos, neuronas, que por medio de pesos y de funciones de activación van pasando la información de entrada de neurona en neurona, de capa en capa, dando como resultado, un resultado que va directo a una función de costo, y dependiendo de la función de costo, pues se mide el desempeño del modelo y se utiliza un optimizador, el cual modifica los parámetros del modelo. Y por supuesto, este es un proceso iterativo, se repite muchas veces, con el objetivo de encontrar patrones en la información, en los datos que se introducieron. Y toco el tema de las redes neuronales porque estos modelos son muy semejantes a los algoritmos variacionales cuánticos. Los algoritmos variacionales cuánticos emplean un optimizador clásico que nos permite entrenar un circuito cuántico parametrizado con el objetivo de obtener una respuesta para un problema dado. En este caso, en mi caso en particular, es la clasificación de imágenes. Entonces, estos clasificadores variacionales cuánticos se pueden dividir principalmente en 3 partes. Una parte de encodificación, una parte de ansatz o, en otras palabras, el circuito parametrizado. Y por último, la medición de los qubits y su optimización por medio de un optimizador clásico. La parte de encodificación básicamente lo que hace es transformar la información clásica a cuántica. Una vez hecho esto, Landsat recibe esta información, realiza las rotaciones pertinentes por medio de compuertas cuánticas y después se mide, entra una función de costo y esta función de costo mide el desempeño del modelo. Una vez hecho esto, pues el optimizador clásico modifica los parámetros de Landsat y de nuevo, esto es un proceso iterativo, se repite una y otra vez hasta que el modelo pueda encontrar parámetros. En estos modelos, la parte de codificación es muy importante y esto me lleva a hablar de las representaciones de imágenes cuánticas. Las representaciones de imágenes cuánticas son modelos de codificación de imágenes basadas en la composición mecánico-cuántica de hardware de computación cuántica. En otras palabras, lo que hacen es, por medio de estos modelos, pasan la información clásica de una imagen digital, por ejemplo, a un estado cuántico. Entonces, este estado cuántico pues, puede ser procesado por el hardware de cómputo cuántico. Y existen muchos ejemplos de estas representaciones. Algunos de esos son el Flexible Representation for Quantum Images, el Null Enhanced Quantum Representation y el Fourier Transform Qubit Representation. Entonces, brevemente quisiera explicarles también cómo funcionan. En el caso de FRQI o Flexible Representation for Quantum Images, básicamente lo que crea es un estado cuántico en el que ciertos qubits tratan de identificar la posición de los píxeles de la imagen y con un qubit extra tratan de almacenar la información de los píxeles o el color de los píxeles en la amplitud de los estados cuánticos. Entonces, el otro modelo del que hablaba, el Null Enhanced Quantum Representation, funciona un poco diferente. También trata de identificar por medio de los qubits las posiciones de los píxeles, pero utiliza más qubits extras para almacenar información de los colores. En una imagen, por ejemplo, usualmente se tiene un rango de 0 a 255 para identificar el color del píxel. En estos casos, necesitaríamos 8 qubits para poder almacenar el color de cada uno de los píxeles. Entonces, podemos ver que es un poco más costoso. Y por último, está la representación que estoy usando yo, que es la representación de qubit de transformada de Fourier. Y esta, de igual forma, trata de utilizar los qubits para identificar las posiciones de los píxeles. Sin embargo, el método de almacenamiento para el color de cada uno de los píxeles es un poco diferente. Digamos que pasa a través de una especie de transformada de Fourier que va como E a la I de alfa de F. F es el rango del color. Y alfa es una constante que nos permite escalar ese color. Entonces, de antemano podemos ver que utiliza un poco menos de píxeles que el FRQI y muchos menos píxeles que el Null Enhanced Quantum Representation. Pero bueno, entonces, ¿qué es lo que estoy haciendo? Básicamente estoy estudiando la implementación y el desempeño de esta representación, de la representación de qubit de la transformada de Fourier como un método de codificación para la clasificación binaria de las imágenes del dataset de MNIS, que son dígitos escritos a mano, y esto usando un clasificador variacional cuántico. Entonces, el objetivo es básicamente introducir una imagen, pasarla por este método de codificación, pasarla por el algoritmo variacional cuántico y eventualmente poder clasificar con accuracies altos esta imagen, ¿no? Y bueno, en principio la hipótesis que teníamos era que estas representaciones de imágenes cuánticas tienen mucho potencial para ser implementadas de forma efectiva como un future map, un método de codificación para la clasificación de imágenes, especialmente cuando hablamos de algoritmos variacionales cuánticos. Y la verdad es que existe muy poca investigación al respecto en el uso de estas representaciones de imágenes cuánticas como métodos de codificación para Quantum Machine Learning. También notamos que responder si una representación de imagen cuántica era buena o mala podría ser parcialmente, por lo menos parcialmente respondida al usarla de forma directa en una aplicación, en este caso aplicaciones de inteligencia artificial. Y por último, se ha visto que un un approach, un acercamiento desde el punto de vista, en los clasificadores variacionales cuánticos, desde el punto de vista de los métodos de encodificación, puede ser mucho más benéfico que desde el punto de vista de los ansatz. Bueno, algunos comentarios breves del trabajo. Lo que estoy utilizando es Qiskit. Básicamente estoy implementando ahí el método de codificación y el algoritmo variacional cuántico. También notar que tuvimos que hacer un downsample de las imágenes, una reducción de la resolución de las imágenes para reducir los costos computacionales y de espacio. Y bueno, los resultados preliminares, la verdad es que son muy prometedores. Pudimos obtener accuracies del más del 90% en el set, en el validation set, lo cual es muy bueno comparado con otros modelos que utilizan métodos de encodificación completamente diferentes. Entonces, son, como dije, resultados bastante prometedores. Y bueno, ya como conclusión, notamos que los resultados preliminares indican un buen desempeño de esta representación de imágenes cuánticas para la clasificación de imágenes. También pues da la oportunidad para explorar otros métodos de encodificación, especialmente las representaciones de imágenes cuánticas, como métodos de encodificación. Y más importante, creo que levanta la pregunta de por qué utilizar este modelo, ¿verdad? ¿Qué modelos son mejores en este caso particular para la clasificación de imágenes? Que si bien es un tema que se ha tratado y he notado que en los últimos 2 años ha llamado mucho la atención, creo que es una pregunta que todavía sigue abierta, pero que su respuesta pues tiene grandes implicaciones por lo menos en el uso en la aplicación de Quantum Machine Learning. Bueno, y eso sería todo. Algunos papers que le pudieran interesar. Gracias.
Muchísimas gracias, Isaac, por esa presentación. Me consta, igual que a ti, ¿no? Posiblemente más que a ti, porque a veces los investigadores vemos cosas que nuestros estudiantes toman su tiempo en poderlas ver. El durísimo trabajo que le has puesto a esto. Gracias por compartir. Y pues con esta plática damos un broche de oro, en verdad, para... Sí, no, lo digo en serio. A este Quantum Latino 2022. Pues si les parece bien, vamos a tomar un minuto de break y a las 5:55 hora de la Ciudad de México y de Bogotá, entremos por favor a la sesión de clausura. So I'm going to switch to English to say goodbye to Isaac. Thank you very much. It was a wonderful and marvelous presentation. I appreciate it. We all appreciate it. And now let's move to the virtual space in which we shall have the closing ceremony of Quantum Latino 2022. Thanks a lot.